Um, this video is explaining arc length and radians, which are brand new to you guys, but they're actually pretty cool and powerful. So first thing we need to talk about before, when we dealt with arcs, for example, we'd have this little arc here, and we'd say, oh, that's, what does it look like, 80 degrees or something? We'd say, it's 80 degrees. We'd just be concerned with the number of degrees in that arc, right? And we'd use that for the arc. So in this case, m would be equal to 80. However, we can do a little better than that. We usually will refer to the arc length with the letter s here. So the length of that arc, right, the total distance of that arc is going to be the total of the whole circle times the fraction that this arc represents. So real quick, if we just use ballpark, let's say 90 degrees because that's easier to visualize. So if this is 90 degrees, that would mean this arc is 1/4 of the way around, right? Because 90 is 1/4 of 360. So it would just be 1/4 of the circumference. So that's where this formula comes from. It's the circumference times the fraction of the whole, or the number of degrees divided by 360, right? We'll do a quick example or two. Yeah, let's get that one. The minute hand of a clock is 6 inches long. We can draw a picture. Sure. Here's my super round clock. The minute hand is 6 inches long. To the nearest tenth of an inch, how far does the tip of the minute hand travel from time progressing from 12 to 12:30? So it starts up here, ba-doop, ba-doop, and it ends up down here, ba-doop, ba-doop. So as it travels, how far did it go? So basically it wants, what is that length or that distance around the clock? Well, how many degrees did it travel? That's the first question to ask. From our picture, we know it's pretty obvious it's 180, right? But how would we calculate that? Well, we know that it's gone 1/2 of the whole, right? Because 30 over 60 is 1/2. And the whole, in this case, in degrees, is 360. So it went 180 degrees. Now we need to plug the 180 back in. It's a little weird here because we just want to use the formula. So the formula requires degrees. If you want to use something else, do your own formula, just intuitive it. That's totally okay. That's cool. But in order to use the formula, we need the number of degrees. So we're going to plug the number of degrees into the formula, which gives us 180 over 360. This brings us back to 1/2. So again, if you just want to figure it out on your own, that's cool. I'm just showing you how to use that specific formula, this one here. And in order to use that formula, you need m, where m is the number of degrees that arc represents. So we have 180 over 360, 1/2 times 2 pi r. 1/2 times 2 pi r. Oh, I forgot to ask you what r is, but r is 6. And we know r is 6 because that's the length of the minute hand of this clock, right? So we have 1/2 times 2 pi times 6. I actually prefer my answer in pi, right? So instead of just getting 3.14 times 2 or 1/2 or whatever, to me it's a lot more valuable if you can keep pi by itself. So 180 over 36 is 1/2, and there's a 2 here, so the 2 and the 1/2 cancel, leaving me with 6 pi. Which is my preferred answer, and I'll give you full credit if you do that 6 pi thing. If you want to punch it into a calculator and get some decimal, sure, power to you. I'll give you points for that too. But just note, to me, this is a cleaner answer because this is 100% precise, whereas this involves some kind of rounding error, even though it may be slightly more intuitive as to actually how large that value is. Cool. So we have our answer, 18.8, or 6 pi. I'll do another one here. Go ahead and see if you can figure this one out real quick. Well, so pause. So 45 minutes here as we're traveling around the clock is 75% or 3/4 of the way around, right? So we take our 3/4 and we multiply that by 2 times pi times r, where r is 8. So 3/4 of 2 times pi times 8. Actually, if you want the nice good answer, what is 3/4 of 8? Well, that's 6, right? I'm going to cross out this, cross out that, put in 6. So that's 6 times 2 times pi, or 12 pi. So it's actually equal to 12 pi is the most accurate answer you can come up with. Although, again, I will accept 37.7. I'm okay with that. Okay, the concentric circles thing is a little weird. The book has a few problems in it, and I don't think you actually need to know it for like many of my tests. But the only thing to note here is that when we have concentric circles, for example, their example here is they have a circle with a radius of 1, a circle with a radius of 2, a circle with a radius of 3, and then they graph these arc lengths, right? So I'll use different colors, I guess. So, and then they graph the arc length of a 90-degree arc. And the only point they're making here is that they're proportional. So the radius of this green arc is 3 times larger than the radius of the purple arc, right? So how many times larger is this arc? It's 3 times, because the radius was 3 times larger. The book goes into, like, makes a little graph. So here's their graph. They graph the radiuses, and they say that, oh, you know, this one had a radius of 1, therefore the arc that it made is this value. The next one had a radius of 2, and the arc that made had that value. Next one had a radius of 3. And when you graph all these, you find they have a linear relationship. It's called like a proportional relationship or linear relationship, direct variation. This isn't a number you need to know, but it's simply 1/2 pi. And I think the reason why they're getting toward that is they're getting toward the radiant stuff, which we'll get to in a second. But this is the type of question that I do think it is important to know. What happens to the arc length when you double the radius? So I'll let you think about that. What happens to the arc length when you double the radius? Well, the arc length doubles, right? Again, the idea being that the arcs are proportional to the radius. So if you double one, you double the other, that sort of thing. That's what I care about, you knowing. Okay. This one here I'm going to do a separate video. So good luck. We'll do a separate video.